Okay, hi everyone, we're here with a question. This question, we have a point mass that is traveling down this triangle and it can go down in two ways. One is along AB plus BC, right? Another one is along AC directly, sliding down the ramp. So we're given that the point mass instantly changes its direction of motion while maintaining the same speed along the horizontal path. So what that means is that AB, when it's over here, right, if it's at B, a split second before is at B, it has some speed u, right, which is downwards, right? It has some speed u downwards, and a split second after reaching B, it has changed its direction, such as moving rightward, right, purely horizontally with the same speed u. Okay, so the velocity changes, the direction of the velocity changes, right, but the magnitude of velocity doesn't change. So we're given this, and we are told to find the angle for which the time taken to go from A to C is the same for both paths, meaning A to B and then B to C is the same as A to C directly. So the first part is quite simple. It's just a bit of standard kinematics and trigonometry. Namely, we want to find the angle, right? We want to find the angle theta such that TAB plus TBC is equal to TAC, right? So we calculate each of these terms individually in terms of the angle theta. And so I'm going to let the length of the hypotenuse here be L. And that would tell us that the vertical height over here is L sine theta. Okay, and the horizontal length over here is L cosine theta. So so TAB, what is TAB? TAB is just the time taken to drop purely vertically under gravitational acceleration g. And that's quite a standard problem, right? So we just have the standard half a t squared equals to s, right? So we rearrange to get t equals to 2s over a square root, right? So over here TAB is just going to be equals to um 2 L sine theta over g, right? L sine theta being the vertical height and g being the gravitational acceleration. So square root that. So that is TAB. Then what is TBC? TBC over here is purely going horizontally. The it's no longer accelerating, right? Because because it's already reached the bottom, so it doesn't accelerate any further. Um and so the speed is constant, right? So namely, what is the speed at V? Sorry, what is the speed at B? The speed at B is just given by conservation of energy, right? So half mv squared, right? V squared equals to uh 2as, right? So V is equals to square root 2as. So s being the vertical, so the time to go from B to C, right, would be the horizontal distance, which is L cosine theta, right? L cosine theta divided by the horizontal velocity, which is going to be square root of 2g L sine theta. And lastly, what is TAC? So TAC is the time taken to go down the ramp, and we can use the fact that when you're going down the ramp, right, there's a few forces acting on you, right? Namely, there's normal contact force and there's gravitational force, right? So in order to get rid of the normal contact force easily, we consider the a basis for the vectors such that the basis we're going to consider is parallel to the slope and perpendicular to the slope, right? So using that, we get a standard result that acceleration down a slope, right, along the parallel component is actually g sine theta, right? And once again, how do you do a sanity check, right? This is just a small tip. How do you do a sanity check? That is sine theta is considering extreme cases, right? In the extreme case that the slope is purely vertical, that's 90 degrees, theta is 90 degrees, then your acceleration is just g, which makes sense. So that's how you can do a quick sanity check for such questions. And I believe that should be standard practice by now. Okay, so anyway, we have g sine theta, so it'll be L over, sorry, no, so the length, the path to the distance to travel is L, right? The distance to travel is L, and so you can apply this, right? So the TAC would be equals to square root of 2L over G sine theta. Okay, so this is a trigo relation, right? L and G are constants. Now we just need to find the theta, right, that makes all this equal. So in order to do so, we can multiply both sides by the 2gl sine square root 2gl sine theta, right? So yeah, so if you do that, then we're gonna get 4 over here is 4L squared sine squared theta square root plus L cosine theta equals to over here it's going to be multiplied by that. We're going to get square root of 4L squared, and the g sine theta cancel. Okay, so simplifying this down, we get 2L sine 2L sine theta plus 2L sine theta plus L cosine theta equals to 2L. Okay, so once again, if we cancel out all the factors of L, then we get 2 sine theta plus cosine theta equals to 2. Okay, so this is, we need to find a theta that satisfies this. So the standard procedure will be to use something like R formula. So R formula allows you to compress these two into R sine of theta plus alpha or something like that, right? But instead of doing that today, I'm gonna show you a small I'm gonna do it another way to get an exact value for theta, right? So in other words, I'm not gonna use R formula because then you can get some decimals and stuff, and I don't really like decimals. As much as possible, I like to keep things in exact form. So I'm gonna rearrange the equation into cosine theta equals to 2 minus sine theta, and now we can make use of the fact that if I square both sides, right? If I square both sides, then cosine squared theta is equals to 1 minus sine squared theta, and the right hand side I just expand it out, and then now I'm going to get a quadratic equation in terms of sine theta, right? And then solving for the roots, I get these two, right? So this gives us two solutions. So what does this solution mean? The solution means sine theta is 1, right? It means that theta is 90 degrees. That means that the ABC triangle looks like that, right? A, B, and C is a degenerate triangle, and that makes sense, right? Because that's one of the solutions, because if B and C are the same points, then of course the time taken to fall down vertically would just be the same. So in reality, we actually kind of want to reject this. I mean, it's not very meaningful to have a degenerate triangle like that, right? So the answer we're actually looking for is this one, sine theta equals to 3 over 5. And so if you arc sine it, then you're gonna get something like 36. Theta is approximately 36.8 degrees to 1 dp, right? Okay, but we're going to work with the exact form as much as possible. So now whenever we see theta, right, in other equations from then on, we're actually going to try to work in terms of sine theta and cosine theta instead, right? So given this, then we can find that cosine theta is equals to 4 over 5, right? So these are the two exact quantities, right? And then of course tangent theta is 3 over 4. So okay, so now for part B, that's where it starts to get interesting. So for part B, we're given that for the same angle theta, right? So we're using the same angle as part 1, as part A. We're using the same angle theta. We for the same angle theta, the point mass moves from A to C via a combination of vertical and horizontal motion within ABC. So what that means is, okay, let me just refresh the page over here so they can clear it. It means that within ABC means that it's actually not traveling inside the triangle, right? And they say clearly there's an infinite number of ways it can be achieved, because yeah, there's infinite number of twists and turns you can do at any point in time. And so they want us to, among all these infinitely many ways, right? They want us to find the path with the longest traveling time and the path with the shortest traveling time. So so how do we begin this? How do we begin thinking about this? We can realize that what's the key observation here is that the speed of the way that the mass can gain speed, right? Let's say the mass is over here. How does it gain speed, right? If it travels purely horizontally, it doesn't gain speed, right? So if it travels horizontally, the speed is constant, right? But if it travels vertically, then it gains speed, okay? It gains speed, and that means that um using the fact that in the end, when it travels from A to C, right? When it travels from A to C, the vertical displacement, right, and the horizontal displacement, no matter what, is always going to be A to B, and the horizontal is always going to be B to C, right? No matter when you twist and turn, no matter when you twist and turn, the total horizontal displacement is always going to be BC, right? Let's say you go like this here, and then like this here, You can see the sum of the horizontal displacements are always BC, sum of the vertical displacements are always AB, right? So using that fact, we can realize that we can kind of think of the total time taken, right, to travel any path as the total time taken to travel the AB path plus the total time taken to travel the BC path, right? Just that some of the it is not exactly going from A to B like this, right? But it's more like going from A to B in this way and then taking a break, right? And then after that it's gonna go from A to B like this, and it's gonna go from the remaining of the path A to B like this. So you can kind of think of these three segments as constituting the vertical component of the motion. So what would that imply? Right, that would imply that I'm gonna first so we did part A already, but I'm actually first gonna do part 2, right? Because that intuition is easier. So part 2 intuition is that shortest time, right? Is the shortest time is actually going to be the shortest time is actually going to be going from A to B and then B to C, right? And the reason is because, right? The reason is because if we go from A to B, right, then the velocity at B is going to be maximum, right? The velocity at B is going to be the fastest, right? If we let's say go from A to some midpoint, let's say I call it M, right? If I start going horizontal, if the point particle chooses to go horizontally at M, right, it's going to have a lower velocity, right, or it's going to have a lower speed than if it chose to go at B, right? And this lower speed, right, is going to in the end, right, this lower speed is going to traverse the horizontal component slower, right? So in essence, you can kind of think of it as if you want the point particle to go from A to C the fastest, the best way is to let it turbocharge, right? Let it charge is as much, let it gain as much speed as possible first, right? In the vertical components, right? Because the vertical components are going to take the same time anyway, right? No matter how many twists and turns you do, the vertical component is always going to take the same time, right? So you want it to gain as much speed as possible so that when it's going to embark on the long journey of the horizontal displacement, right, it can have the biggest speed to to traverse the horizontal displacement. So in essence, you want to wait for it to fall all the way from A to B, and then B is at the maximal speed, then you travel B to C, right? As opposed to let's say A to M, then you travel something like that, then later you let it fall further, and then you travel. Then you have lost this. You have used some slower speed, right? At this M because the speed at M is less than the speed at B. Okay, so that's the idea. You can make it regress, but I think it's fairly intuitive that you want it to gain as much speed as possible before it starts to traverse the horizontal part, right? So in other words, the motion is just from A to B purely vertically, and then from B to C purely horizontally. And we know from part A, right? We know from part A that um we have found the angle for which that is equals to sliding down the slope AC, right? So the time taken is just sliding as if it's sliding down, right? Slope AC, which is just 2L, remember L being the length of the hypotenuse, um 2L over g sine theta, right? Where g sine theta is the acceleration down the slope. Okay, so if you plug it in, you get essentially the factor of square root 10 over 3, right? So in general, the answer is going to be in terms of square root L over G, right? That's what gives us the time dimension, but the constant in front, right? The dimensionless constant in front is going to be the thing that we're comparing most of the time in this question. And in this case, the dimension constant is square root 10 over 3, and most of the time it's in surds form. So as much as possible, I like to leave it in exact form, right? But if you simplify down, you get this number to 5SF. Okay, so that's it for part 2, right? Part 2 is that, right? Part 3 is going to be the ratio of the two times. So basically, if you know part 1 and part 2, then you automatically get part 3 for free. So what is part 1 then? How do you do B part 1? So B part 1 is the interesting part. Okay, so B part 1, we are told to find the longest traveling time, right? So as our intuition said, right? The earlier we choose to change direction, right, the slower it would be, right? The earlier we choose to change direction, the slower it will be. And yeah, so we the idea for achieving the longest time possible is to is to take a very little after a very short distance, right? After a very short distance, you want to quickly twist already. You want to twist and change a direction, right? So after, let's say, a very infinitesimally small distance of going vertically, you want to change it such that it go horizontally. And then after that, you're gonna hit this AC hypotenuse, and they say that horizontal motion within ABC, right? So you cannot leave the triangle ABC. So after you hit the hypotenuse here, you're gonna want to drop down further, right, and gain a bit of speed, right? Much to your unhappiness, right? Much to the point particle's unhappiness, because you want to take the longest time possible, but it's going to gain a bit of speed, right? And it's going to go horizontally again, right? So the very moment you drop something a little bit, then you're going to go horizontally, and basically the infinitesimal motion is to go something like that, right? Okay, so it's something like that, right? Basically you're hugging the hypotenuse in this way. Okay, so of course this is you want to do it in the limit that all these tiny little triangles, they 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 go they shrink to an infinitesimally small size. Okay, so there's two methods to think about this question. I'm going to say what the first method is going to be what I'm going through first, which is more rigorous, and it's also the method I prefer, right? But the second method is a method based on the idea of average velocity, and the idea actually requires a bit of justification. So the idea technically will get you to answer faster, right? But I want to go through the rigorous method first, so we put it firm in foundation that we are confident that that's our answer. And then when we do the other method, right, it's more of a, oh, you can use this shortcut um because because of some nice mathematical properties about the velocity. So first of all, what's the first method? So the first method, okay, I'm gonna expand it out over here. The first method is going to be calculating an integral. Okay, so um to achieve the longest time BC, right? Remember what's the motion that we're looking for? We're looking for a motion where, okay, so this is our triangle. We're looking for a motion that zigzags down the hypotenuse in this way, right? So what's the total time taken to traverse the horizontal part from B to C, right? What's the longest possible time? The longest possible time would be, right, imagine breaking down each segment, right, each of the horizontals, the entire BC into many small segments highlighted in red, right? Each of these segments, I'm going to call them infinitesimal length dx. Okay, so each one of these small red bars is dx, and that's and each of the dx is going to take some time to traverse, right? And how much time is it going to traverse? It's going to take time, right, of dx over, right, distance over speed, right? So speed in this case is purely horizontal, right? In this case, I'm going to call it that the speed is actually is Vx, right? But remember, Vx is a function of position, right? Because as you go further and further down, the horizontal axis, right? As it goes from here, the speed here is, the first one is going to be different, very different from the speed further down, right? And as it goes further and further down, the speed is actually going to increase, right? And what's nice is that actually, given a particular x coordinate, right? Let's say we're at this x coordinate, right? What's the horizontal speed? The horizontal speed is actually just the vertical speed at the x coordinate, right? Because remember that when we zoom in a bit, right? The horizontal speed, like I'm gonna highlight it in yellow here. The horizontal speed at this segment is actually equals to the the vertical speed right before it twists into that segment, right? I'm gonna put it in orange here. It's gonna be, as it's traveling down this vertical segment, is going to be the speed at the orange part is actually going to be the speed at the yellow part, right? So as this Vx is actually just Vy, right? And why do I want Vy? It's because Vy is a function of x, right? This Vy, which is the orange one, this Vy is actually going to be easier to calculate using conservation of energy. Okay, so yeah, Vx is we don't have a form, we don't have expression for it, but we know what Vy is because we can use how much distance it has traveled down, right? And then we can use conservation of energy from there, right? So this quantity over here is how much time it requires to travel a particular small segment dx. Okay, and so if we integrate um right, from x equals to 0 to x equals to L cosine theta, right? If we integrate from x equals to 0, x equals also cosine theta of dx over vyx, right? We're gonna get the time taken. Okay, and the reason why we chose bounds of L cosine theta is because these are coordinates, right? We're integrating over the variable x, right? And hence the two endpoints of the integration needs to be coordinates for x, right? It needs to be x values for x. Okay, so remember, um just a reminder, as always, whatever variable you're integrating over, you write a differential. Whatever variable you're integrating over needs to be the bounds of the integral, right? If not, your integral doesn't make sense. So okay, so how do we express Vy in terms of x, right? It's actually just square root of 2g x tangent theta. So x tangent theta, right? If you are a particular okay, so actually the x in this case, I'm actually letting go the other way around. So it's actually x actually goes leftward. So if you have a particular x over here, then your height, right? Your height would be, oh, sorry. What am I saying? The x variable is actually going from left to right, right? So if I'm a particular x, right, then the vertical velocity, right, is going to be the however much I've fallen, right? And however much I've fallen, right, at this x, however much I've fallen is going to be x tangent theta. Okay, so yeah, so v squared equals to 2as, right? So a is just g and s is just x tangent theta. Okay, so that is now we have an integral that we just need to evaluate. So how do we proceed with this integral? We realize that the integral is just okay, yeah. How do we proceed with this integral? Sorry, I had to sneeze over there. Right, but we realize that the integral is just 1 over square root x. So we integrate it, we get this, right? And substituting the endpoints using the fact that cosine theta is equals to 4 over 5. Then when we evaluate the integral, we get this. Okay? And simplifying it down in terms of surds, we're gonna get longest time to travel BC is 4 square root 2 over 15. So yeah, so that remember this number because we're gonna derive this answer soon in another way. Okay, so once again, that's the longest time to travel BC, and the time to travel AB is fixed, right? You cannot change how fast you travel vertically, yeah, because yeah, so it's just gonna be fixed at 2 square root of 2 L sine theta over G, right? And if you evaluate it out, you get this third form, right? This dimensionless constant, right? So all in all, the answer to B is this one, right? Is this plus this, okay? And if you evaluate it out in terms of numerical, you get this answer. So yeah, so that's the longest time possible. And this is a very foolproof way, right? This is you reason out using integrals. There's no way you can very mathematically rigorous, right? But there's actually a shortcut, which is that so this is one of the suggested solutions also. Another observation is actually you can realize that, okay, I'm going to zoom in here and make an argument, right? You can realize that if I imagine, right now I'm an observer, and instead of observing, the motion like that and using one stopwatch, I'm actually going to use two stopwatches, right? So I have two clocks. I'm going to say one of them is for the x, right? And I'm going to call that x, tx, right? X time. And the other one I'm going to call ty, right? For y time. So I'm going to use two stopwatches instead of one stopwatch, right? And the reason why I do this will be apparent soon, right? But the x stopwatch will measure how much time it takes to traverse the x components, right? So for example, you measure this part plus this part plus this part and this part and so on. Okay, and the y stopwatch is going to measure how much time it requires to travel the y components. So it's going to be this one plus this one plus this one plus this one plus this one. So imagine I have two stopwatches in hand, right? When I watch it go down, right, when I watch it go down in a zigzag motion along the hypotenuse, then I'm gonna press and press both at once, right? So I'm gonna start the y stopwatch, right? I'm going to start the y clock when it's released here to here, and then when it reaches the bottom here, right, I'm going to stop the y stopwatch, right, stop the y time, and I'm going to start recording the x time, right? And then as I'm going to record the time it takes to go from here to here, and then after that, when it reaches here, I'm going to stop the x time, and I'm going to start measuring the y time. So I imagine I'm alternating between of course I'm gonna click very fast, right? But I'm gonna start measuring those kind of times. And the reason why is because I mean, all in all, the total time is just going to be the sum of the tx plus ty, right? But we can actually make some arguments about the motion um, for tx, right? So if you look at it, right, we know that the motion for ty, right, how does it look like if we take all of those, right, and we're going to piece it all together? So it's just going to drop like this, and going to drop like this, and going to drop like this, and drop like this. So imagine I take all the vertical, right, ty times, and I piece it all together. Then what does it look like? It looks like it's falling at constant acceleration g, right? Then question now, what if I take all the x times and I piece it together? The answer is actually it's going to look like it's traveling at horizontal acceleration g tangent theta. Okay, and why is that so? Here's why I say so. So once again, coordinate. Establish a coordinate such that x is moving to the right, right? X is rightward positive. Then, if I look at the longest time TBC, right, it looks something like that, right? And namely, this integral form can be rewritten as this differential form, right? Or rather, this derivative form, right? Differential equation form. So we're gonna see that this is dx over dtx, right? Tx being the horizontal time, right? As in red, right? Dx over dtx is equals to this, right? This is just a rearrangement from the above equation, right? Then what do we know about vyx? Vyx is this form, right? As established earlier, because yeah, by using trigonometry and v squared equals to 2as. Okay, so when we look at this, right? Actually, what this is, right, is what are we actually doing here? When we're actually doing this integral, what we're actually doing is we're saying TBC is equals to integral from 0 to TBC of dt, right? And then based on that, dt, right, is actually equals to 0 to the length of BC, right? Dx over v over this velocity, right? This 2gx tangent theta. Right, that's what we're doing, right? But this is you can kind of think of this as kinematics in the horizontal direction, right? So what I mean is that if we look at this differential equation, right, we look at now this differential equation, right, with dx over dt, right, tx to be specific, but yeah, dx over dtx is equals to this thing, right? And it's, you see there's x on the right hand side, so actually this is a differential equation, and we actually are very familiar with this differential equation, right? You might not see it, but actually this is constant acceleration differential equation, right? So if put the ansatz, right, it'll be very obvious, right? If I put ansatz of this, right, x as a function of tx is equals to some acceleration, right, times tx squared. Then if I plug the ansatz back into the differential equation and solve it, I'm actually going to get an expression for ax is equals to g tangent theta. So what this means is that if we not only did our stopwatch, right? Not only if we not only used our stopwatch to record the times, but let's say I took a video of it, right? And I happen to start the video when it goes horizontally, starts going horizontally, and I stop the video when it starts going vertically. And then I start the video when it starts going horizontally, and stop the video when it starts going vertically, and so on, right? Then after that, I'm gonna piece together all the videos together, and you're actually gonna see that it's just accelerating. That you're gonna see that it obeys this differential equation, right? And based on that, you're actually gonna see that um it actually it's as if it's constant acceleration motion to the right, right? So basically, the entire motion, right, as it's hugging this hypotenuse, right? The entire motion is as if it's vertical acceleration of g, right, as we already expected, but the entire motion actually can be seen as horizontal acceleration, right, g tangent theta. Okay, so that's the idea. And what do we know about after that? We can just use x equals to half at squared, right, to get the following answer. Okay, so we get back the same 4 square root 2 over 15, right? The same factor as before, but this you can see that this is a conceptual change. There's a difference in conceptual ideas, right? In the previous method, right? The previous method, we got the answer for sure, right? But we did this integral, and then we realized, oh, it's an integral of 1 over square root. But yeah, so there's not much intuition here besides a bit of math, right? But over here we have new intuition now. We have new intuition that as it's going horizontally, right, it's as if it's constant acceleration motion, right? And namely, right, I believe the suggested solution that you have in another PDF, right? The suggested solution actually uses average horizontal speed, right? So it actually considers the horizontal speed, right, at the start, right, which is 0, right? No, initially no horizontal speed, and horizontal speed at the end, which is square root of 1.2 GL, right, which is actually just equals to square root of 2 G 3 over 5 L. Okay, so yeah, so you see them use horizontal speed, the average horizontal speed, right? And then maybe you're wondering, why is the average horizontal speed justified? And the answer is that the average horizontal speed thing is justified because, right, we have s equals to u plus v over 2 t, right, one of the Suvat equations, except that remember that to use this equation, right, to use use average speed, right, you need to make sure the acceleration is constant, right? If acceleration is not constant, then you cannot do this. And it turns out horizontal motion acceleration is in fact constant, so you can use this s equals to u plus v over 2t. Okay, so I think that's a point that is very interesting, right? Because it tells us that, oh, the horizontal motion is actually just at constant acceleration motion, right? So yeah, so I hope that I hope that I hope you learn some intuition from this, right? Sometimes constant acceleration motion, right? Suvat equations are hiding where you're not looking. Okay, so with that, right, we know that the answer is just the rest of the for my second method, the rest of the working is the same, right? TAB is the same. Um, yeah, TAB is the same, and so in the end, the ratio we're gonna get is something like that, right? So if you actually work out the ratio in exact form, you're actually gonna get 7 over 5. Okay, so yeah, so using certs and stuff, you actually get 7 over 5. So anyway, yeah, that brings us to the end of this video, and I hope that you found this video interesting. Okay, so yeah, thank you, bye.